Welcome back, everyone. DevOps Pro Conference 2022. I'm Kevin Jacob. I'm your host for today. I'm a DevOps consultant at FE Code, and today we have Filipe Oliveira to discuss about end-to-end performance testing, profiling, and analysis at Redis. Let's hear from him and learn what they do at Redis. Philip, would you like to go and share your screen?
Yes.
Wonderful.
So let's start.
While Philip does that, make sure to use the Q&A and chat boxes to ask your questions. Yep, your screen is visible and you're ready to go, Philip.
Okay. Thank you, Kevin. So, hi everyone. Good morning, good afternoon, and good night, depending on the place you're watching us. So today I'm here to talk about our approach to end-to-end performance testing, profiling, and analysis at Redis. To give you a little bit of context of who am I, I've been working on, I work at Redis on continuous profiling, mainly on continuous profiling and on improving the code base of our projects. I've been at the company for about 3 years, and apart from it, or apart from the main projects that we foster and that we develop in-house, we also contribute a lot to the community. And I'm basically, apart from the main projects, one of the main contributors to two very special projects, or two sketching data structures that, one of them we use, for example, to increase the latency tracking on Redis itself. So, but I'll give more context out of during this presentation. But before we go deeper on the slides, I'm going to share a little bit of the agenda for today. So basically, I'll start by describing what we mean when we talk about performance at Redis, our old behavior, or the behavior, or the more manual behavior that we used to have when we did performance analysis at the company, the do's and don'ts that, we found out by our experience, our approach, or how we fixed the issues from the past, and what we aim for the future. So let's start by describing what we mean by performance at Redis. We have two big groups of work in the company. Let's say that we focus on the open source project itself. We call it Vanilla Redis, and it's mainly a purely open source project. And our work there as a performance engineer and as a member of the performance team is to foster any observability and benchmark standards across the community, not only across the company or the companies that are developing Redis, but across the community and all vendors. Support the contribution of anyone who wants to submit a PR to Redis. For example, we are there to help in terms of understanding if the PR that user is making will affect the performance, will improve the performance, how is it affecting, basically explain the numbers and explain the code. And let's say our end goal is to keep Redis fast and to optimize it as much as we can. That's, let's say, for the Vanilla Redis project or the Vanilla Redis area. And then we have the company based products, let's say, or the projects that started in Redis company itself. And in there we have even more responsibility. Let's say, not only we have to maintain and develop product features, we also need to make sure that everything that we contribute to keeps the performance in a good shape. Or bottom line, we need to raise awareness and make sure that the performance is kept in a good shape across all company projects. We need to empower developers to give them as much independence and as much ability to improve the performance on their side without requiring any manual intervention from the performance team. We need to, as I said, intercept regressions, so to make sure that we keep a steady, stable, and a good performance product. We need to understand, let's say, the baseline of new features that we are going to deliver. And bottom line, on a quick sentence, basically improve the performance of all the products that we care about. And to give a bit of context, why is this a little bit hard? Not only in the company that I'm currently at, but I guess that everybody looking or watching this session can relate to this. So bottom line, normally on our company products or even on open source products, every project, let's say, we have extensive amount of functional tests, a very large amount of functional tests. We have, let's say, products that even have like 100% coverage in terms of functional testing. But then when we talk about keeping track of the performance of the project itself during time, we always require, let's say, manual intervention. We need to devote time to deploy environment or deploy stable environments, get some numbers, and then decide if the feature that we are working on or if the version of the product that we are going to release is in good shape or not in terms of performance. Functionally, everything is automated. When we talk about performance, things are not so much automated. We are way behind in terms of what we have for doing performance analysis versus doing functional analysis of our code. And to give a little bit of context why this matters to us and to put things in the context of the company itself, I'm going to present an old case from Redis from 2019. One of our projects or one of the products is Redis Search. It's a model, one of the, let's say, the most used and the most major models that we have at the company. And in 2019, this is a simple performance task in which we are basically bumping the minor version of Redis Search from 1.4 to 1.6, and associated with this bumping in the version, we need to assess if the performance is in good shape or if we improve the performance or if we detect some variations, etc. And bottom line, this implied manual work. We had a set of benchmark utilities that we ran to produce numbers and to analyze how a baseline versus comparison, how did the performance change, and then we decided and iterated over the results. Bottom line, as I said, this was a simple request or the simplest request that we can have in terms of performance analysis. And I basically enumerated why this was so hard for us or why this called for action in terms of automating the performance analysis. Because bottom line, in the past, it took us more than one day to, let's say, to provide feedback to the developer teams that were working on the product. For example, they did some change, they improved something, we ran the benchmarks manually, and then we iterated over the results with them. But the feedback cycle implied a lot of manual steps associated with this, given that normally the common case in the companies is that we have a lot of developer teams versus one or two performance teams devoted to doing this analysis. So we always need to prioritize the tasks that are related to performance and make sure that given that we have multiple projects requesting the same stuff, this one-day feedback cycle can even get increased, let's say. One other consequence or one thing that we wanted to avoid that we saw in the past is that this performance analysis was very sealed. So let's say that the information was kept under the performance team. So the amount of data that sits on the developer team versus the amount of data that we had in terms of performance on the performance team was different. So we didn't. There was no one-to-one match in terms of the knowledge that we had in terms of performance and the knowledge that we shared. And ultimately, what we wanted to be a fast check took several months from the start of the work. Let's say the start of the version, which was 1.6.0, up until we improved it to the point in which we are confident that we have like a good product in terms of performance, not only in terms of features, but in terms of performance. It took more than 3 months to achieve it. Bottom line, at the end, we achieved our goal, which was to improve the performance of the product, but this came, this type of task came with a cost. So, and I think that you can all relate to this set of sentences or to this analysis, is that, predicting the amount of time that we will be spending on this type of tasks, even that seemed simple at the beginning, is one of the hardest things that we can do. Because bottom line, on this type of request of performance check on version A versus version B, given that they buffered a lot of potential issues and they buffered a lot of work in a single analysis, the amount of time that the prediction of how much time it will take us to, let's say, detect a regression, fix it, etc. It's very hard to do. So as I said, we were basically doing manual checks or doing a reduced number of manual checks. It's just buffering potential issues, and we wanted to avoid it. And we came to a plan, or this was our target, let's say. In the left side of the slides, you can check the initial position of the performance check in the past. So we basically waited up until we had a preview release of the entire set of features that we wanted to release. Then we did a manual check, and then we finally released. This implied potentially multiple iterations, multiple fixes, and a lot of stressful work, given that we are at the end of the pipeline. So it implied a lot of work up until reaching the performance check, and we had a bit of time to up until the point in which we are, or up until the release date that we already committed before. So this was the previous behavior and the previous way of doing performance checks at the company. And what we wanted, or what we aim for, and what we are doing right now, is that we are doing an initial performance check with the minimum amount of code change possible. So let's say we move from having a preview build that contained a lot of code changes to the minimum amount of stable changes, which is basically a PR with a specific feature in which we kept track of its performance even before approving that code change to master, let's say. So we move from one single point in time big performance check to multiple zero touch or zero manual work performance checks as soon as we had the code change feasible to be tested. And this is not, as a quick side note, this is not something that we are disrupting. This is not like something that we are the only ones pushing forward. So this is being done by a long time by some of our competitors even. So Elastic has it, Lucene has it, and they are both very open about their benchmark specs, which is something that I find extremely useful to push forward standard specs with regards to the product, with regards to the features that they provide. MongoDB as well, and I deeply recommend you guys to check how they are approaching the end-to-end performance testing, which I believe, it's something that they are doing in a very advanced manner, and I think that they basically sorted it out in a very elegant manner. But I think that what they are missing there, that we basically can contribute, and then we are basically being disruptive about, is to basically provide ways to improve the code or to detect potential points of improvement in an automated manner. We are not just interested about keeping track of performance, but we are also interested about explaining why we are getting those numbers and how we can improve them. So I believe that this is the real disruptive thing that we are doing at Redis, which is also automating the part of profiling and the part of understanding potential points of improvements on the code. And so this is basically, from this point forward, I'm going to focus on how we got to this end-to-end automated performance analysis. And we are doing this into, let's say, two groups, two lanes of work. The first one, it's fully devoted to the open source project, and is being done with the Redis developer group. So not only the company, the Redis limited company is working on it, but AWS, Ericsson, Alibaba, everybody that contributes to the open source project is included in this, with the addition of other partners. For example, Intel is our most devoted partner to this effort, and we are using all our knowledge to basically create an open source spec that you guys can check. And bottom line, the spec is the standard that we are trying to foster. So the first phase of having an end-to-end performance analysis platform was, first, let's define what we consider to be good use case use cases to be tracked over time and to basically analyze. So we've open sourced the spec. It currently contains 56 independent benchmarks that we can keep that we use to keep track of Redis performance, and we use it in several manners: for historical purposes, for doing regression analysis, and for feeding your documents. And keeping track or triggering a performance benchmark on the Redis project is as simple as basically labeling a PR with action run benchmark. So apart from keeping track of important branches like the unstable branch, or keeping track of version tags in which we automatically trigger performance checks, we also give the ability to the Redis maintainers to basically trigger a benchmark on demand if they feel that the change on that PR needs to be analyzed, or if they feel that that's interesting data that should be retrieved. And as I said, so we basically run the benchmarks and provide information broken by branch and by version. So we can, even if you add a new benchmark to the specification, we can re-trigger for historical purposes all versions or point in time in the past, so that we can have so that we can give you the information, for example, of how did Redis 3.2 version performed on this specific benchmark, even though we are just adding this benchmark now. So we have the ability to do that. And for so that's by the by version breakdown that we allow, and we consider that the by branch breakdown is more interesting for let's say regression analysis, in which we are constantly, even before releasing, keeping track of the performance of Redis. And then we have like the lane 2, or the lane in which it's just Redis, the company, reading it. And we decided to approach this into two different manners, because we consider that this lane B, or this group of work, in here we can move a lot faster and we can experiment a lot faster, because it's just us deciding what to do and pushing things forward. So let's say that in here we are a little bit more advanced than what we have already on the open source project, but mainly because we want to experiment faster. And then when we consider that we have everything sorted out, we apply the same ways of doing performance analysis to the larger project, which implies a lot more responsibility, for example. So as I said, we started by small projects, or the incubation projects, which are basically the Redis models. We focus initially on everything related to open source. So everything that I'm discussing here, anyone can trigger a benchmark, a steady stable benchmark with our automation. So everything is open source, from the benchmark runner, the benchmark clients, everything. Everybody is able to replicate our results. And we allow for local and remote triggers. As I said before, basically we focus on the open source data, and in the same manner that we allow for by branch and by version breakdown of the performance data, we also allow for something that we consider scalability analysis. So to understand how well do we scale when we, for example, increase the number of shards on Redis, and when we swap the machines, etc. So we are not just interested about the keeping track of performance over time. We also want to understand what's basically the inflection point in which a specific benchmark will stop scaling. As I said, we allow for local and remote triggers of the benchmark. So, for example, a developer adding a new benchmark can validate if everything is working as expected on his local machine, and with the same benchmark utilities, he can trigger a remote benchmark, a steady stable benchmark, which implies deploying steady stable VMs on AWS, stable VMs that we have basically configured to produce the most deterministic results possible with the less amount of noise possible. And with that remote triggering of data and constant feed of data, we basically automated the part of associating associating a performance trigger, a performance benchmark to every commit. And this is an example of multiple ways that we are automatically triggering benchmarks. So one of them is basically keeping track of the performance over a nightly basis. And so even if we don't do any active change on the repo, we trigger a set of benchmarks every day to produce enough data for us to be able to say that the benchmark is stable, and for us to be able to keep track of the performance of that specific project over time. And we also automatically trigger everything that we consider important in terms of performance. So every feature that we release on the project, that we are working on the product, we trigger automated benchmarks, even on development cycle. So as long as, or on the first push to a feature branch on GitHub, we trigger a benchmark. So let's say that we are doing multiple iterations of that same feature. You can assess from the first moment what's the performance of that specific feature and how is that going to impact the overall performance of the product. Similarly, we also trigger everything that starts by perf and everything that starts by version. So we are basically keeping track of everything that matters for us in terms of regression analysis and baseline analysis. And as I said, we use this data in a very active manner. So we don't need to wait for the pre-release or a release of a product to understand what's the performance or how is the performance going to change. Even before merging to master, we can produce a baseline versus comparison table like this, in which we have all test cases, or let's say one test case per row, and we provide you what's the baseline performance in terms of a specific metric that you consider, for example, the percent of 50 latency of the server, the achievable ops per second. So we allow for different metrics to be showcased, and we allow for different metrics to be used for the comparison. And we basically provide you a baseline value with the expected variance or with the variance of results for multiple runs, and the comparison in the same manner. And then we do a differential analysis between both of the results. It's important to say that we also assess how stable the results are. So, for example, if we consider if you look at the table on the baseline column, you see not only one value, but how did it vary on that same version. So, for example, if we see that there's a lot of variance either on the baseline or on the comparison, we discard that data because we consider it's unstable for us to do a decision upon. So we provided this information in an automated manner. And then we can also do associated with the tests, we trigger also the same set of benchmarks, but with the profiler attached. A side note is that we don't use the results of a benchmark with the profiler probe attached, because normally profiling implies overhead on the system that's being profiled. So basically, we discard all the benchmark results out of it, and we just use the profile data or the profile artifacts that were generated. And out of the box, let's say with zero touch, we produce 6 different benchmark outputs, and they are all related to on CPU profiling. And as you see in the next slide, there are basically one of our to-dos is to extend the analysis to outside of the CPU, but for example, off CPU analysis, mocking analysis, etc. But right now, we only provide automated information with regards to on CPU analysis, and we provide you the entire frame chart of the specific benchmark and the main thread or the main thread frame chart of that same benchmark. So so that we can split between background work and main thread work and understand what are the potential points of improvement in a split view. We also provide you what are the top CPU consumers in terms of on a by shared library a breakdown, by shared library and symbol, so shared library and function, and also up to the line of code. We also provide the 5th profiling artifact is related to identical steps collapsed, and we basically can use it for doing a differential analysis. But that's something that we will focus in the next slides. And then if we detect a hot path, or let's say if we detect a path in the code that's consuming the majority of the CPU time, we also provide you the call graph with that information. So as I said, we have a frame chart. We have the breakdown by shared library, breakdown by shared library and function, and the very interesting, or the thing that I believe it's more useful in terms of development or active development based on profile data is the breakdown by line of code. You can go as granular as possible and understand, okay, out of this function, that's, for example, taking 15% of the CPU time that we can see on point number 3, out of that function, what's the line of code that really matters to me? And we can see that on the bullet number 4, you see that 12.4% of the CPU time is being spent on a single line of code, which is line 16 of that specific file. So this is very useful information and information that we generate out of the box. There's no manual intervention of any performance engineer to produce this data. And as I said, we also, if we detect a call graph, we identify it and provide it to the developers. So how do we use this data? So now that we have this huge amount of data with different breakdowns of information, we try to use it not only for fixing performance regressions, but also to do proactive optimization. Or let's say that we proactively try to improve the performance of the specific project on our code. So in this slide, you can see an example of an analysis and the PR that basically resulted out of this initial analysis. I suggest you guys, at the end, I'll share the slides. I suggest that you guys see it so that you understand how we are deterministically, let's say, improving the performance of a specific project without, let's say, waiting for a regression to be introduced, or without, without having a control of the performance path of a specific project. So now to try to close let's say the session so that we can have like time for Q&A. Up until now, I believe that what we gained was that we deeply reduced with this information and with this automation, we deeply reduced the feedback cycle. So we moved from days to have this type of information with the manual work to a single hour to produce this offset of artifacts and offset of performance data that developers can use themselves without having an initial, or without having to ask for a performance engineer to guide them through this initial data. So I would say that the 60 seconds performance data is already provided in an automated manner. As I said, they don't. The developers don't rely upon a performance engineer to add further tests. Up until now, doing a holistic view or an aggregated view of the number of benchmark suites that we provide, we have 240 full benchmark suites being constantly run over time without manual intervention, and the developer can easily add more tests. Even the community on that benchmark spec that I shared, they can easily add a new set of benchmarks with a new tool, as long as it's producing stable results. And there's no manual work from the performance team, so this can clearly scale. And the interesting part is that not only we scale, but we are able to devote time to more interesting subjects. So we don't spend our work days doing manual stuff or stuff that's not very interesting in terms of performance analysis. So we say that we automated the boring stuff, and we can now focus on analyzing the data, which is much more interesting than focusing time just producing it, let's say. And ultimately, what we basically ended up reaching was that we were able to find much more performance points of improvement than with a single manual work, because basically we are having a huge amount of data produced in an automated manner, and we are able to focus on analyzing it instead of producing that same data. Something that we can very easily do right now is also not only test our code, but let's say test the infrastructure that we are using within our production environments, etc. Let's say that to put in a very simple sentence, we can very easily test if moving, for example, an AWS VM type from M5 to M6i will produce better results for a specific product. So we don't need to wait. You can very easily A/B test not only the code, but also the infrastructure that you are running with, and use this information to relate to something useful for product, let's say. As I said, there's like a continuous feed of updated numbers. So there's no requirement for the performance team to be constantly doing the same stuff. And as an ultimate benefit is that we are much more open, or we are fostering an really open and really unbiased way of doing benchmarks, because everybody can reproduce it. Everybody can see what we are doing, understand if that's a fair benchmark, and if not, propose something to improve the spec. So now it's not only the responsibility, it's not only on the performance team to generate, let's say, open numbers and unbiased numbers. Everybody can participate, and we use this amount of data and the amount of knowledge that the community has to improve Redis in a fair manner, let's say. What's next? So bottom line, well, this is not perfect. We haven't reached a state in which we can say, okay, everything is automated, everything is running without issues. So we want to basically first have a feature parity between what we have on our most advanced projects in terms of performance with open source. So I see that everything that we do within the company, it's basically even with the open source platform that we have and the open source specs. We want us all to share the same infrastructure, to share the same way of doing performance analysis, because bottom line, we will all gain from it. And as I said, as I said before, we want to extend our visibility of what's going on off the CPU. Right now, we are deeply focused on CPU analysis, and we want to extend it off CPU analysis, threading, walking, and also start extending it to do some more interesting stuff, like, for example, understanding potential points of improvement in terms of vectorizing the code, using vectorization reports that can already be produced in an automated manner to try to improve the code blocks of our projects in a manner that they will be vectorized and implicitly improve the performance. And basically, what I said is this entire breakdown all summarizes to getting more visibility and to removing a lot of unknowns in terms of performance analysis. And then apart from this improval of the visibility, we also want to make sure that in the same manner that we are producing more and more data, we are advancing in terms of detecting a regression in an easier manner, let's say. We don't want just to do a point-in-time check or baseline versus comparison check. We want to be able to analyze trends and to be more precise in terms of providing an answer to where a regression entered the code. And bottom line, ultimately increasing the open source and community adoption and exposing everything that we have, not only on the Grafana, that's already being used by members of the Redis developer group and our other partners and ourselves, but we want everything to be open. We want anyone who wants to be able to assess the performance results by themselves and to basically correlate that performance data with their specific use cases and how they use Redis. And with this, this set of goals for the future, I basically end this talk. And as an ending side note, if you are interested about what I've described up until now, we are hiring, and we have 2 open positions specifically for the performance team that's handling this type of stuff within Redis. So I'll be more than welcome to receive you guys and to follow up with you on the performance at redis.com email.
That's wonderful. Thank you very much, Philip.
Thank you, Kevin.
I was looking at the Q&A and chat session right now. Don't see any questions there, at least for now. I hope. Let's wait for a couple more seconds and see if you have any questions. Meanwhile, would you mind dropping your LinkedIn handle or Twitter handle in the chat so that
Yes.
any interested candidates can reach out to you, or maybe if you have some questions or discussions to be taken further on this topic.
Okay, so I'm sending right away my LinkedIn and my Twitter handle. Okay, and I'm also sending them the careers link of the company. so that anyone that's interested to check it out. But well, either please go ahead.
That's wonderful. Thank you very much. Great. Very nice. So I'm sorry I interrupted you. You were saying something.
No problem. Well, I was just finalizing, stating that either via LinkedIn, Twitter, or even the Redis, the company webpage, reach out. We are more than welcome to receive your questions and if you are interested, apply for the performance jobs.
Nice. In that case, I will end the session. No, we have a question. What is the maximum throughput you saw in Redis?
Okay, so we have an open document that was released like 3 years ago, in which we reached 200 million ops per second at sub-millisecond latencies, meaning that you can reach 200 million ops per second, and each operation taking less than 1 millisecond to be received on the client side. But bottom line, this is just a ballpark number. We just stopped it because it was starting to get more and more expensive to increase the number of machines that we use to produce this set of results. If you notice, there's an easy way, or Redis scales via sharding, in which we basically split database among multiple processes, or in which each process contains a small portion of the data. So let's say for scaling, you just need to increase the number of machines and split increase the number of shards and divide them across the machines that you are using. So bottom line, Redis, and given that there's no communication that's inter-process communication that we use to be able to answer, let's say, a command to the database, this scales linearly. Well, this really scales linearly because there's no way of it not to scale linearly up to the point in which you reach a point of saturation either on the network or on the CPU or memory. So bottom line, the 200 million ops per second was just a ballpark number, but we can keep increasing it. We just need to add more and more VMs. It will start getting more and more expensive. But the interesting part is that to answer in an easy manner the question, well, we've reached 200 million per second, but we can reach much, much more. It's just a point of, let's say, scaling more and more and more, because there's no real limitation towards scaling within Redis.
Great. Thank you, Philip.
My pleasure.
So
I'll share the link of the benchmark that you just described on the chat. Okay, so here it is. It describes how it was reached. I'm not sure if, maybe on the chat, right? Sorry, I sent it on the Q&A. Setting on both sides.
Nice. That's okay. Wonderful. That has been given thumbs up by Mathia, I guess. Really nice. So in that case, I will close the session, and thank you very much for having you here, and have a nice rest of the day, Philip.
Thank you. Have a nice day, you too, and thank you for watching the session. Bye bye.
This brings to the end of the data management practices track. Have a nice day. That is it.